Okay, class. So today we will learn about image resampling and interpolation. Okay, so image scaling. If you look at this right image, actually this image is quite big, and when you try to fit into this screen, and some of the top part and the bottom part are cut off. So if this image is too big to fit on the screen, how can we generate a half-size version? So we have to apply the image subsampling. So the idea is based on the original image, we try to pick up the important pixels or the key pixels to do the subsampling and then use it in the new image. So in this left image, actually it's a half size of the original image that we have seen just now. And the idea is to throw away every other row and column to create a half size image. And this process is called the image subsampling. So you're trying to get the key pixels from the original image. Then you create a new image, which is a half size of the original image. Same goes to the middle image, which is the quarter of the original image. And you reduce it using the, for example, the left image, you resize it half and it will become the quarter image. And then same goes to the last image, which is 1/8 of the original image. And when you look at this image of different size, the left one is the half size, the middle one is the quarter size, but you zoom in 2 times, so that is having the same size as the left image. And the last image, the right image, you zoom in 4 times. So when you are having the same size as the half size, you will see the image looks so crafty or blur because we lost a lot of information when we try to zoom in a smaller image to a larger image. And this is another example. The left image is the original image, right image is the subsampling image. You can see the building has a lot of blurring effect, or what we call the aliasing. And this is even worse for the synthetic image. So synthetic image is created using the computer software like Adobe Photoshop, Pen software. Yeah, and then in between the boxes, you will see a lot of zigzag lines. These are the problem for the this image subassembling. So what is aliasing? And if you have a 1D signals, and then you will see this kind of signal pattern. And if your sampling rate is not high enough, you will fail to capture the details of your your signal. Same goes to your image. If your sampling rate is not high enough, then you are not able to capture the amount of details in your image. It will give you the wrong signal or image, or what we call the layers. So all this effect is a layers effect, and the same goes to this one. And last time we have this audio CD, and when you want to listen a song, usually the this CD is using 44.1 kilohertz sampling rate. Why? Because it's 2 times of the human hearing sampling rate. human hearing is usually around 20 kilohertz. Your times 2 is around 40 kilohertz. So in order to do the sampling right, you need to understand the structure of your signal or image. You can try to watch this YouTube video, and it's talking about how to apply this Fourier transform. So from this Monsieur Fourier, and the idea is try to remove the noise when you convert it into different signals. And then to avoid the aliasings, usually the sampling rate must be larger or equal to 2 times of the maximum frequency in the image. Or if we say another way, is larger or equal to 2 samples per cycles. So this minimum sampling rate is called Nyquist rate. And there is something what we call the wagon wheel effect. So if you look at this image on the left hand side, we have this frame 0, and then we put a marker on top so that we know when the wheel is rotating. And if we have this camera and then we try to capture, on frame 0 it looks like this, and then frame 1 you try to rotate it in clockwise directions. Frame 2 the angle change again, frame 3 and frame 4, so we know it's rotating according to the clockwise. And then without the dot, if you look at this process, the wheel will appears to be rotating slowly backwards or counterclockwise. And you can look at this link for the descriptions, and I'll show you a video. So over this image, we had this outer wheel and the inner wheel. So we know now this whole wheel actually is rotating according to the clockwise. But when the speed is getting higher and higher, and then we will observe the outer and inner wheels are rotating in different directions. So this is the typical example of the wagon wheel effect. Yeah, so now I can see the wheel is outer layer is rotating anti-clockwise, and the inner one is the clockwise directions. And another one is what we call the temporal aliasings, which is this helicopter plates. Because this helicopter plate is rotating in a high frequency, but our camera sensor is low frequency. So actually we cannot capture the rotating process. And this is from this YouTube video. Same goes to the some example where we capture using our smartphone. When you look at the center area, you will see a lot of this line effect. Yeah, this is also a aliasing effect. And then also this right video, look at the floor, there are a lot of paper noise on the floor. And same goes to the root. You see the root area, there are a lot of blurring lines. Yeah, so actually this is the frequency cannot actually follow the real situation or the real environments. So when talk about this Nyquist limit for an image, for 2D example, so usually the idea is 2 times of the your image patterns. So all these dot on the image is the sampling or the sample you use to generate a new image. So when we're referring to this top row, and this is what we call a good sampling, because on every black and white pixel, actually we have a sample, and we want to generate a new image, then we will have a very good result. But if you look at the bottom row, this is what we call the back sampling example. Because whenever we want to generate a real image, we are using we lost some information, because you can see for this image, the dot is only on the black pixel. Actually, there are also other white pixel and black pixel. Same goes to this image. Some are missing. So whenever we use this kind of a low frequency rate to generate a new image, then we lost some important information. That's why in this Nyquist limit, it say you're trying to get more samples or 2 times of the maximum frequency of your current image, so that you can generate a better image. And for aliasings, when downsampling by a factor of 2, original image has 5 frequency that are too high. So how can we fix this? And so the idea is we can filter the image using a Gaussian filter, and then we do the subsampling. So for example, in this image, the process actually is it went through the Gaussian filtering and then subsampling. And then Gaussian filtering, subsampling, Gaussian filtering and subsampling. So by using this method, actually we can get a better output, or we can generate a better subsample image. So you look at this result. This is a half size of the image, quarter, and it's 1 over 8. So all these are applied using the Gaussian, compared to this one is without using the Gaussians. So actually we can preserve more details from the original image. So the solution is you filter the image first, and then you do the subsampling. So H is your filter, F0 here is your original image. So you blur it, and then you subsample it. Blur it, then you subsample it. Same goes with the other. And in this way, we will generate what we call the Gaussian pyramid. Level 0 is your original image. Level 1 is the half size of the original image. So for each of these level, we will apply this blurring and then subsampling in order to get a better subsample image. This one is proposed by Lambert and Adelson on 1983 Gaussian pyramid. So we have this level 0 up to level n times n. Level k. Level k is your smallest size. And this Gaussian pyramid have also application in computer vision. So here is a question. How much space does a Gaussian pyramid take compared to the original image? So if we keep applying the Gaussian filter and then perform the subsampling, then we will generate a new image which is a half size of the original image. And then we add it up. So at the end, we have a 4/3 the amount of space as the original image. And then if we have this checkerboard image, so what will happen when you apply? Or you make the checkerboard smaller and smaller. And the left-hand image is a naive subsampling method. And right image, you apply the Gaussian filter and then do the subsampling. So you can see the area where the boxes is very, very small. It will turn to gray because it's trying to average of the black and white squares. And each pixel actually contain both. So this is a way to reduce the aliasing effect, or what we call the anti-aliasing. So that's for the image subsampling method. And next we look at the upsampling. So your image is too small for this screen, something like this. How can we make this image 10 times bigger? So the simplest approach is we can repeat each row and column 10 times. So wherever your original image is from here, then you just repeat every row and every column 10 times this original image. And this is using the neighbor pixel. So the method is called nearest neighbor interpolation method. So for example, in this figures, the x-axis is your pixels value. So you have a pixel 1, pixel 2, pixel 3, pixel 4, pixel 5. So when you form an image, you will have a different pixel value for different pixels. And an image actually is a discrete point sampling of a continuous functions. So you could somehow reconstruct the original function. Any new image could be generated at any resolution and scale. So if we draw a line to connect all these points, and the pixels, the new pixel, let's say we want to upsample this image. So we want to estimate the new pixels among the neighborhood pixels, for example, from 1 to 2. And we can roughly estimate the new pixels from these neighborhood pixels. So what if we don't know the pixel values of the f? So we can guess an approximations. So just now we draw a line to collect all these pixels, and actually there are different ways to calculate the in-between pixels. And we can use a filtering method. And then we convert this f to a continuous functions. So f is your the image generated. So you have f functions. And then you apply a filter on your original image. So we reconstruct by convolution with a reconstruction filters. And then you will have a new image. So this is how we can assemble the image. This is your, the F bar is your new image. This is your original image. And we can use a triangle, a linear interpolations. Just calculate the average in between these two pixels. And there are many ways to do the image interpolation. So given the original image as this the hand size, so you apply the different filters. So ideal case is we use scene functions to do the estimation. The common one is we have this nearest neighbor interpolation, which is a box method. So you allow the pixels value So all these dot 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 actually is your original pixel value. You draw a box around it. Then in this way, you can count, estimate the neighborhood pixels. For linear interpolation is using 2 points, and you estimate your center points. And then for Gaussian reconstruction, you apply a Gaussian filter. So what does a 2D version of these hack functions look like? So this is a linear functions, linear interpolation using 2 pixels. And then if you have a bilinear interpolation, you use 4 pixels. Yeah, so it will look something like a pyramid. And then we also have the bicubic. So bicubic usually using 16 pixels to estimate the new pixel. And this is a summary of the different methods. So you have a nearest neighbor interpolations, linear interpolation, bilinear, bicubic, then cost. So this one is with a larger window. So when your quality is getting better, and then your speed will getting smaller, slower. So original image is something like this. You want to make it 10 times bigger. If you apply the nearest neighbor interpolation, you will have this left image. So you see the image has a lot of pixelated effect. And if you use a bilinear interpolation, the result is slightly better, smooth, and bicubic is even better. And then when we use this image interpolation, so often we use it for the resampling. For example, the resizing, rotating. When rotate the image, you want to estimate the new location of the image. You do a warping. You perform the translation and scaling on the image, and also perform the perspective transform. So this one, you also changing the depth of the image. Usually warping we use 3 points, and then perspective transform we use 4 points to do the transformation. And then you also can use interpolation for zooming in or zooming out. And on top of that, we also use interpolation for generating the vector image. So if you look at this image, if we without these interpolations, you will see a lot of this zigzag effect around the border. And then with this vector space graphic, then you will have this right image. And it's a slightly different from the pixel-based image. So no matter how you zoom in the image or make it smaller, the image is always smooth and sharp. So one typical example is you generate the vector graphic from points, lines, curves, polygons, and use some mathematical equations. And last time I used EPS to write a paper, image, figure, or the graphic pictures. Yeah, because usually in the PDF file, when you zoom in the image, they want to see the details. So you have to use this kind of vector-based graphic in order to keep the image quality clear and precise. So EPS is a good way to generate this kind of vector-based graphic. And why is this vector graphic useful? Because resolution is independence. So no matter how big or how small, the quality is always clear and sharp, scalable infinitely, and usually smaller for simple graphic. We use this kind of vector-based graphic to generate the company logos, the icons, CAD drawings, and also fonts. And you can zoom forever without pixelation problem. And also in games, people use interpolation to de-pixelating the pixel art. Yeah, you have this, I think nowadays there are many games using this kind of icons. Yeah, so if you want to make the image sharper or in a low resolution, you can always use an interpolation method. And in the modern methods, the popular one is what we call the image super resolution. The idea is we try to make the image clearer and sharper. So if you have the 2K or 4K or even 8K TV in home, so usually this method is applied in the end. Whenever we want to show the video on the TV screen, we want something that looks clearer and sharper, because a human eye is very intelligent, can differentiate whenever there is some blurring effect or pixelated effect on the TV videos or image. Yeah, so this technology can help you to increase the image quality. So super resolution usually you have multiple images or a burst of photos. For Google Pixel or maybe iPhone, I think you can capture a sequence of images. And then with these sequence images, you can really create a better super resolution image. And the last image is effect of the hand tremor, where I think the hand is shaking. So you can see there are a lot of this aliasing effect. And then on the right image, is image you capture with and without the super resolution zoom. So it will clear. You can see sometimes this image become blurred. That is without the super resolution. And with, you can see the detail. So in summary, the key points in this lecture is we can do the subsampling of image, and usually will cause the aliasing problem. So better is to blur it first, to remove the high frequency, then downsample. And if you repeatedly blur and downsample by 2 times, you get a Gaussian pyramid. And if you want to do upsampling an image, it requires interpolation, because you want to fill in the image with more pixels. So you need to guess what is the next new pixels you're going to fill in. And this can be posed as a convolution with a reconstruction kernel. Okay, that's all for this lecture.